Welcome to the exciting world of algorithms. Have you ever wondered how your smartphone knows what to suggest next? Or how a search engine finds the most relevant information in seconds? The answer lies in algorithms. Today we are going to explore what exactly an algorithm is, its representation, characteristics, and the difference between an algorithm and program. So grab your notebooks and let's get started. An algorithm is simply defined as a step-by-step procedure or a set of rules which is designed to solve a specific problem or to perform a task. From navigating your route with GPS to recommending your next favorite movie, algorithms are everywhere. They ensure our digital experiences seamless and efficient. An algorithm must always terminate after a finite number of steps. This ensures that we can expect a solution in a reasonable time frame. This property is known as finiteness. In this property, no infinite loops are allowed, so in algorithms, we need to set a clear termination point. Next, each step of an algorithm must be precisely defined, ensuring that the actions to be performed are clear and unambiguous. This property is known as definiteness. Definiteness is crucial because it allows anyone following the algorithm to understand exactly what to do next at each stage. Without precise definitions, the probability of misinterpretation increases, leading to errors and inefficiencies. When every step is clearly defined, the algorithm becomes easier to implement, debug, and share. It sets standards for consistency and reliability, which is essential in programming and problem solving. Next, a good algorithm should be able to solve not just one specific problem, but a whole class of problems. This property is known as generality, and the versatility makes algorithms powerful tools across various applications. Next, let's talk about inputs. An algorithm should accept a zero or more inputs. These inputs are values or data provided to an algorithm for processing. For instance, consider an algorithm designed to calculate the average of list of numbers. It requires input values to perform the calculation. However, in some cases, an algorithm might not need any inputs at all, like an algorithm that generates a random number. Next, an algorithm must produce one or more outputs as a result of its processing. Outputs are the final result or data generated after the algorithm has processed the inputs. In the previous example of algorithm that calculate the sum of list of numbers, the output will be the total sum. This output provides a valuable information that can be further used for decision making or analysis. Having a well-defined output helps to ensure that the information provided is useful and actionable. Whether it's a number, text, or visual representations, clear outputs enhance the overall effectiveness of the algorithm. Next, an algorithm should produce the correct output for all valid inputs. This means that when you provide an algorithm with acceptable data, it should consistently deliver the expected results. This property is known as correctness. This is critical because it ensures reliability in algorithms' performance. An incorrect algorithm can lead to significant errors, especially in applications like finance, healthcare, and any field where accurate data processing is essential. Now, let's discuss about effectiveness. An algorithm is said to be effective if each of its steps can be executed in a finite amount of time and with a clear understanding of what to do. This ensures that anyone can implement the algorithm without confusion. By ensuring that each step is executable and clear, we create an algorithm that are not only functional but also user-friendly. This increases the usability across various applications from simple tasks to complex problem solving. Finally, Let's talk about the efficiency. An efficient algorithm makes optimal use of resources, such as time or number of operations and the memory to perform the given task. Consider two algorithms for sorting a list of numbers. One algorithm might take a few seconds to sort a large list, while another might complete the task in just milliseconds. The faster algorithm is more efficient as it requires less time to achieve the same result. Efficiency is critical in algorithm design, especially as the size of input data increases. An algorithm that performs well with small datasets may be impractical with larger ones if it is not optimized. To evaluate an algorithm efficiency, we often use metrics like time complexity and space complexity. Time complexity measures how the execution time of an algorithm grows with the size of input, while space complexity assesses the amount of memory used. Now that we understand what algorithms are and their properties, let's explore how we represent them. Effective representation is a key to communicating our algorithm clearly. First, we have natural language. This method uses plain, everyday language to describe the steps involved and make it easy to understand. While natural languages are accessible, it can sometimes lead to ambiguity. For instance, consider this algorithm for finding the maximum of two numbers. In the first step, it will compare two numbers, and in the second step returns the larger number. Here, the steps are straightforward, but without precise definitions. Different interpretation may arise. Therefore, while natural languages are great for initial explanations, it's important to clarify any potential ambiguities. Next up is pseudocode, a powerful tool for outlining algorithms. Pseudocode combines elements of natural language with programming constructs, creating a structured yet informal way to describe the steps involved. It's not meant to be executed like actual code. Pseudocode provides a clear and logical outline that's easy to understand. Let's take a look at an example for finding the maximum of two numbers using pseudocode. Here, we see the structures clearly laid out. The function findMax takes two inputs, x and y, and uses a simple conditional statement to determine which number is larger. This approach offers clarity while allowing for flexibility in how we express our logic, making it an excellent choice for both teaching an algorithm and drafting solution before implementation. Next, we have flowcharts. It's a dynamic way to visually represent algorithms. Flowcharts use a variety of symbols to denote different operations, decisions, and the flow of control. This visual representation is particularly beneficial for visual learners, as it transforms abstract concepts into an easy way to follow diagrams. In flowchart, each symbol has a specific meaning. For instance, ovals represent the start and end points, rectangles indicate process, and diamonds show decision points. Here is a simple example. A flowchart to find the maximum of two numbers. It clearly outlines the steps, showing how the flow control moves from one step to another, making it easy to visualize the decision-making process. Next, we'll explore a unified modeling language, and is commonly known as UML diagram. It is a standardized modeling language used to visualize the design of a system. It encompasses a variety of diagram types that represent different aspects of a system, making it a versatile tool for software engineering and algorithm representation. Now that we have explored what algorithms are, including their characteristics and how we represent them, it's time to dive into something practical. Let's take a look at an example that puts all this theory into action. First, the algorithm takes two inputs. These are referred to as A and B. Then, it performs the addition of these two numbers, which is calculating their sum. Finally, the algorithm produces the result of this output. So, this algorithm clearly outlines a step-by-step procedure for adding two numbers. The second example of another fundamental algorithm is finding the maximum of two numbers. This algorithm is essential for determining which of two values is larger. First, we start with our input, two numbers, which are x and y. The first step is to compare x and y, and this is where we determine which number is greater. Next, we check if x is greater than y. We will output x. This means x is larger number. However, if x is not greater than y, we move to the next step. In this case, we'll output y as a larger number. And finally, we'll output the result, which is the larger of two numbers. This algorithm effectively helps us to find the maximum of two numbers by following these clear steps: compare, decide, and output.